So, we will continue with our analysis of first order logic, and today we will study a kind of proof mechanism called resolution refutation proofs. So, today's lecture will be on resolution refutation proofs. The basic idea of resolution refutation is as follows. We will first convert the set of rules and facts into clause form, and recall that in the last class we had discussed that a clause form is a conjunction of clauses, and each of these clauses can be a disjunction of predicates or their negations. So, that is the clause form. In the clause form we have only the universal quantifiers, and all of those universal quantifiers are pushed to the left. So, any variable that we have in the clause form is universally quantified from the outside, right. For the existential quantifiers, recall that we used a thing called skolemization to replace the existentially quantified variable by skolem functions. So, after converting the set of rules and facts into clause form, we insert the negation of the goal as another clause, and we try to use resolution to deduce a refutation. So, let us see what I think we had discussed this in the context of propositional logic. The idea is that if I have a set of clauses C1 and C2 and some Ck, suppose this is the set of k clauses that are given to us, and we want to deduce whether this implies the goal, right. So, then if this has to be valid, then the negation, then it is equivalent to writing not of this C1 and Ck or G is valid, right, or the negation of this, which means C1 Ck and not of G is, if this is valid, then the negation of this is unsatisfiable. Okay. So, if we can deduce that this thing is conflicting, in the sense that from this if we are able to deduce false, that means that this set of clauses will be inconsistent and therefore unsatisfiable, and therefore this original thing that we wanted to prove will be proved, right. So, if we use resolution to deduce refutation, then if a refutation is obtained, then the goal can be deduced from the set of facts and rules. But recall that because of the semi decidability of first order logic, it may also be possible that we continue forever and we are not able to deduce false, right, and that resolution continues forever, and that will happen for the kind of formulas that I had shown you previously, that which has functions within the predicates, and there is a recursion in the function which never terminates. So, in the last class we had studied the conversion to normal form, where we had seen a set of steps that converts any given formula to normal form. So, like taking the existential closure and eliminating redundant quantifiers, then renaming any variable that is quantified more than once, eliminating implication, then moving negation all the way inwards to the predicates, pushing the quantifiers to the right, then eliminating existential quantifiers as I was mentioning through a skolem function, which is also called skolemization, followed by moving all universal quantifiers to the left, and finally distributing the and over or to get the conjunctive normal form, and finally an optional step to simplify, so that in the end we get a set of clauses. So, here for example this not Px or Qx Gx is one clause and not of PFA is another clause. So let us take an example. Okay, then we had resolution, which in terms of the I have rewritten the resolution rule. We had seen the resolution rule in the implicational form in the last class. I have just rewritten it so that we can associate the resolution rule with the conjunctive normal form that we are looking at. So suppose this is one clause which is a disjunction of some of these predicates, and this is another clause which is another disjunction of predicates, and then theta is a substitution which unifies Zj and not of Qk, which means that if we use the substitution theta, then Zj here and not of Qk here become identical. So if that happens, then the resolution tells us that we can deduce the OR of Z1 through Zi minus 1 and Zi plus 1 through Zm, and likewise Q1 through Qk or Qk plus 1 through Qn. Now that's easy to see, because if you have something here, if you have some A here and not of A here, then we know that if you merge the two, if you take AND of this clause and this clause, you can get this clause by eliminating that A, right. So this is the same resolution rule, but only shown in the clause form, right. So what we are going to do is, we will take one full example and work out a complete resolution refutation proof, and then we will study some of the optimizations that we can do in the proof procedure. See, essentially the proof procedure is a search procedure, because we are going to have a set of clauses, right. Then you can take pairs of clauses, use resolution to deduce new clauses. Now which pairs will you take? There are some pairs existing in the knowledge base, some which you have deduced, right. If you continue using them in a haphazard way, then we will have to do a lot of work. So the search is essentially to choose those pairs on which we will apply resolution and eventually be able to deduce false, right. And we will see some heuristics which will help us in choosing the clauses, so that we are able to deduce false more quickly. Okay, so this example is inspired from some very well known stories. Okay, so the first sentence says that Harry, Ron and Draco are students of Hogwarts School of Wizards. Every student is either wicked or is a good Quidditch player, or both. No Quidditch player likes rain and all wicked students like potions. Draco dislikes whatever Harry likes and likes whatever Harry dislikes. Draco likes rain and potions. And the goal is that, is there a student who is good in Quidditch but not in potions, right? And we are trying to find out whether this is true or not, whether this is valid or not, whether the set of clauses helps us in deducing that there is a student who is good in Quidditch but not in potions, right. So first thing that we are going to do is to write each of these sentences in first order logic and reduce them to clause form. Now the nice thing about the clause form is that you have all these sentences, each of them are going to give you some clauses, and the entire clause form is just the conjunction of all these clauses. So we can take one sentence at a time, convert it to clause form, take the next sentence, convert it to clause form, and then append all the clauses together to get the full clause form, right. So first sentence is Harry, Ron and Draco are students of Hogwarts School of Wizards. So let us say we have a predicate called student, right. So the first three clauses that we will have are student Harry, then we will have student Ron, and we have okay. So these are our first three clauses. Then next sentence says that every student is either wicked or is a good Quidditch player or both. Every student is either wicked or is a good Quidditch player or both. So we can write this as for all x student x implies either wicked, so wicked x, or is good or is a good Quidditch player. So let us call that predicate Quidditch itself. Right, but this is not in clause form. So if we convert it to clause form, what we will get is, we will convert this to remove this implication. So we will have not student x or wicked x or right. So let us name these clauses. So this was C1, this is C2, this is C3, this is our C4. Right. We are not writing the for all x outside because it is implied, because in clause form all the variables will be will be universally quantified. Right. Then let us look at the third statement. It says no Quidditch player likes rain and all wicked students like potions. So this is actually two sentences, and let us write them down. The first sentence says that no Quidditch player likes rain. So which means that for all x, yes, implies right, implies not of right, and the other one is sorry, let me write this as x comma rain, and this predicate says that x likes rain. So likes xy is x likes y, right, and then we have that all wicked students like potions. So for all x right. So again, if we convert this to clause form, then we will have C5 which is not of Quidditch x, or then not this is C5, and then we have C6 which is not of right. Then we have Draco likes whatever Harry likes and likes whatever Harry dislikes. So, this is going to be like for all x and in clause form we will have again two clauses. So, let us call them C7, which says that not likes Harry X or not likes Draco X, and C8 which says just check out, this is for one side of the implication, this is for the other side of the implication. Then finally, we have Draco likes rain and potions. So, that is going to give us another two clauses. So, C9 which says likes and C10 So, these 10 clauses form the knowledge base. The knowledge base currently consists of these clauses C1 through C10, right. Now, we will encode the goal and insert the negation of the goal into the knowledge base and try to deduce a refutation. So, the goal says, is there a student who is good in Quidditch, but not in potions? So, if we have to write that in first order logic, we will say there exists X who is good in Quidditch. So, and does not like potions. So, if we convert this, if we take the negation of this is goal, this is the goal G, then not of G is for all x, then okay. So, this is the goal clause, not G clause, which we will insert into the knowledge base as C11, right. So, this is going to be our C11. And then we will try to reduce false. And for deducing false, we will use resolution, and if you recall that in the last class we had mentioned that resolution is a complete proof procedure. So, if false can be deduced at all, then if we repeatedly apply resolution, we should be able to deduce it. If we systematically apply resolution, we should be able to deduce it. So, let us look at one way of deducing this. So, we will start with two clauses. We will start with likes. I am just showing one way of doing this deduction. Then we will see that what are the strategies for systematically doing this deduction. So, likes Draco quotients is given to us. Right. And we have, this is one clause, and then we have not likes Harry X or not likes Draco X. Now, if we apply resolution on this, then we see that this and this will unify with the substitution of x by quotients, and when this unifies, because this is the negation of this, so therefore, we will just have not likes Harry quotients. So, what resolution helps us in deducing from this by substituting x by quotients is not likes right. Then we also have not Quidditch X or likes X quotients. This is another clause that we have. Recall, we had this clause not Quidditch X or likes X quotients. This is which clause? Yes, this is the not of the goal, right. So, we use that clause with this, and again with X substituted by quotients, we will have unification between these two, and so with resolution we will be able to, we will get not okay. Now, because of lack of space, I am not being able to draw the full tree on the other side. So, I will break it up and draw it separately in another thing. What I am going to do is, I will use this not likes Harry quotients to unify with other things also, right. So, I will carry over this one, this clause into the next page, and I will start with not likes Harry quotients. See, this is something which we have already deduced. So, I can use it again to resolve with other clauses. This we have already deduced from these two. So, now we can, it is now there in the knowledge base. So, I can use that with say we have this clause not of wicked x or likes x portions. We can resolve these two to get, what will we get? Right. So, we will leave this up to here for the time being, and then pick up two other clauses from the knowledge base and deduce something else, and then come back to this. We have deduced not wicked Harry. Previously we had deduced here that not Quidditch Harry, right. Now let us see, we have in the knowledge base student Harry, and we also have in the knowledge base not of student x or wicked x or this was another clause that was there. In fact, the first clause which told us that a student is either wicked or good in Quidditch. So, if we use these two with x substituted by Harry, then what do we get? We have wicked Harry or right. Now, having deduced this, we will go back to the previous one where we had deduced not wicked Harry. So, we have not wicked Harry here and we have wicked Harry or Quidditch Harry here. So, let us say that if we use these two, then resolving with these two will give us Quidditch Harry, right. So, if we use this and let us give this clause a name, let us say CA, then with CA and this I am able to reduce Quidditch Harry, right, and then we have not Quidditch Harry here. So, if we use these two, so let us call this CB, then with CB and this gives us false. Yes. You can do that also, depending on how your theorem prover can handle clauses. It may be able to resolve more than pairs of clauses at the same time. That is quite acceptable, and in fact, some theorem provers will do that. So, what we have seen so far is that we converted the rules and facts into clause form, and then saw one way to deduce false. Right. Now, we can use this resolution in many different ways also. This is one particular proof tree, and the proof tree of this whole thing is actually the concatenation of all these 3 pages that I have done here. So, it is a tree which eventually leads down to false. Right. Now, what we want is a short proof tree. We do not want to derive things which we are not going to use for deducing the false, but how do we do that? How do we direct the proof mechanism towards the false? So, there has been several suggestions of doing this. These are called different resolution strategies, and these strategies are meant for making the search for the false more efficient. Okay. The first one that we are going to look at is unit resolution. Now, what this tells us is that every resolution step must involve a unit clause. What is a unit clause? A clause which does not have any or, it just has one predicate or its negation. Those are the unit clauses. So, every resolution step must involve a unit clause. Let us look at the resolution that we did just now, and then you will see that this is a case of unit resolution. If you look at the text, please. See, we started with these two, and here this was a unit clause. Then after doing that, the second step was these two, and again this is a unit clause, right. Then we deduce this. This is also a unit clause. Here also this is an unit clause, right. What we deduced was another unit clause. Then this is a unit clause, and then CA was this one, which is a unit clause, and CB was another unit clause. This is also a unit clause. So, at every step of the resolution, at least one of the clauses was a unit clause. So, that is what unit resolution aims to do. And as it turns out that when this was originally proposed, unit resolution, it gave a dramatic speed up in the proof mechanism. So, it usually leads to a good speed up, but at the same time it is incomplete in general. What do we mean by incomplete? No. By incomplete we mean that there will be examples, there will be cases where you should be able to deduce the proof or deduce the goal, but using unit resolution you will not be able to do so. So, there can be cases where if you just use a unit clause in every step of resolution, you will not be able to prove the result. So, that is what is meant by the incompleteness of unit resolution, right. Recall that whenever we are talking about completeness, it is always completeness on one side. So, if it can be deduced, we should be able to deduce it. If it cannot be deduced, we may not terminate. We have to live with that for first order logic. So, unit resolution is incomplete in general, but it is complete for Horn knowledge basis. You remember what is meant by Horn knowledge basis? Where you do not have, in the implication form, you have on the left hand side you have on the right side you have only one literal, or you do not have any ORs on the right hand side, right. So, that is Horn logic. So, if we use Horn logic, yes, because if you have ANDs, you can break it down into two rules. Suppose I have A implies B and C, then I can break it down into A implies B and A implies C, right, and those two individually are fine. So, having ANDs on the right hand side is not a problem, but we cannot allow A implies B or C. That is something which Horn logic will not allow, right. We will study first order Horn logic called prologue in the following lecture we will start prologue. This is a completely new kind of language that we will study, and that uses this Horn logic for doing the deduction. So, it is not as powerful as full first order logic, but it is something which is a fragment of first order logic. Then there is a strategy called input resolution. Now, what this says is every resolution step must involve a input sentence from the query or the knowledge base. What does this mean? It means that whenever we use resolution, we must use one of the clauses which was there in the original knowledge base, including the query. No, you cannot resolve, this prevents you from resolving two derived clauses. And the notion behind this is that, see, what we have in the knowledge base, that is what is going to lead us to false, right. So, we are going to always try to use those rather than trying to resolve two derived clauses. Okay. And typically we will start with the goal. We will start with the goal clause, because assuming that the knowledge base itself was consistent, addition of the goal is expected to make it inconsistent if we have to derive false. So, whatever derivation takes place must take place around this goal that we have inserted. So, we will start from the goal and keep on doing this resolution. At each step, at least one of the clauses should be from the original knowledge base or the goal, right. Now, if you look at the derivation that we did just now, this was not input resolution. Why? Because if you see that in some places, let us look at this. Here it is fine because these were there in the original knowledge base. Here this was in the original knowledge base, so this step is also fine. But when we use, say, okay, this is also fine, right, but then when we do this, this is a derived clause CA, which is not of Wicked Harry, and this is also a derived clause which is Wicked Harry and Quidditch Harry or Quidditch Harry, and this step of resolution is not, is against input resolution. Input resolution will not allow you to do this, right. Okay. You have to use always at every step one of the, at least one of the clauses from the original knowledge base. Now, in Horn knowledge bases, modus ponens is a kind of input resolution strategy, because modus ponens is what, you have something implies something, A implies B and you are given A, then you deduce B, right. So, one of those rules are part of the knowledge base. So, every time you are using a rule to deduce something, so it is a kind of input resolution. It is again incomplete in general and complete for Horn knowledge bases. But there is a generalization of input resolution which is complete, and let us see what that is. Yes.
Here it might be possible that we have we don't have a correct sequence of applying these clauses, and maybe the all inputs are over and we haven't reached to the solution.
Yes.
And maybe after doing means after read the means we haven't read the solution, but now we can use derived clauses and can read the solution. But
yes, yes, that is why this is incomplete. That is why input resolution is incomplete. There are examples where by using derived clauses you will be able to deduce false, but if you just stick to input resolution you will not be able to deduce it, right. That is why it is incomplete, but it is complete for Horn knowledge bases, because you always have that set of clauses implies something else, which is essentially modus ponens, right. So, for Horn clauses this is always, this is a complete proof procedure, otherwise it is not. So, the generalization of input resolution which is complete is called linear resolution. Now, what generalization do we do? We will allow clauses P and Q to be resolved together either if P is in the original knowledge base, which is as in input resolution, or if P is an ancestor of Q in the proof tree. So, in the proof tree we are taking clauses, deriving something out of them, then using this one with some other clauses, deriving something out of them, and so on. So, at every point of time the two clauses that you will resolve, one of them has to be either from the original knowledge base, or it can be one which we have derived on this path of the proof tree. So, it is an ancestor in the proof tree. If we use that, that is fine, and we will be able to do this. As it turns out, that linear resolution is complete. Let us quickly see whether the example that we have done can be derived using linear resolution. Actually, this particular case can be derived using input resolution also, but in general input resolution is not complete, but linear resolution is complete. Please take some time to think about why linear resolution is complete, but input resolution is not. So, this simple generalization which allows us to use the ancestor clauses in the proof tree makes the resolution procedure complete. So, how will you show that it is complete? Take any resolution proof and try to convert it into an equivalent linear resolution proof. If you are able to do that, then that means that linear resolution is complete. Okay. Just take some time off to think and work this out on your own, right. Okay, let us quickly apply linear resolution on this. So, we will start with the goal. The goal clause was not of Quidditch or right. This was the goal clause, and we will resolve it with not student X or and that is going to give us again this linear resolution can be done in multiple ways. I am just showing one way of doing it, right. Then we will resolve again with student Harry. So far we are using one clause always from the input, so it is input resolution as well, right. This were from the original knowledge base, now we are using this which is from the original knowledge base. So, with this we derive wicked Harry or See, what this linear resolution helps us in doing is that, because you are not going to use two derived clauses unless they are on the same path of the tree. So, the tree is not going to branch out a lot, the tree is not going to branch out a lot, it is going to be something like a linear tree, right. So, that also helps us in keeping the knowledge base, size of the knowledge base contained, because if the knowledge base size starts growing, then we will end up in trouble. So, here we have wicked Harry and likes Harry potions, and we will resolve this with text, please. We will resolve this with again, this is from the original knowledge base. So, we use this and this to get right, and then we will use these two together will give us this is not likes right, and we have in the knowledge base we have not likes Draco potions, this gives us right. So, this whole thing is the proof tree, starting right from here when we had this derivation, then we end up to false. Now, this whole derivation, at every step we have used one of the clauses from the original knowledge base. We started with the goal and kept using one clause from the knowledge base until we deduced false. So, this is both both input resolution as well as linear resolution. If any proof is satisfies input resolution, it by default satisfies linear resolution, but the reverse is not true, and probably I will reserve it for your exam to give you some case which will work for linear resolution, but not for input resolution. So, please try to think that how to discover that this is going to be the case, right. So, with that we come to the end of this particular lecture, and we also come to the end of our analysis of first order logic. In the next lecture I will start with the language Prolog, which is a logic programming language, and we will see how to write different kinds of programs with Prolog. Okay. And after finishing off with Prolog, then we will start the planning, the chapters on planning. Right. The whole of or a major part of the analysis of artificial intelligence is centered around search. That is why we started with search. Search is the most basic, the basic mechanism which allows us to solve these things. As you can see now, this is also a kind of search. Deduction is also a kind of search, where you have to search within the rules and facts and clauses, and to search and find out the appropriate order in which to apply them to deduce this. We will see later on a little bit of constraint logic programming, where with deduction we will be able to use also constraints, and there has been recent annotations to constraint logic programming which allows you to solve optimization problems as we did in heuristic search using a deductive framework. So, the deductive framework is just an interface to write what we want to do using a logic, and the solver is at the back end, right. In procedural languages, the solver that you have is the von Neumann architecture, which does this fetch, decode, execute cycle. We know that after this statement is going to be executed. So, that is one flow that we understand and which we believe is the core of computation, right. Now, logic programming is does the computation in a different way. So, you have to write the program knowing that the computation will happen that way, right. So, in the next lecture we will start off with logic programming. Right. So, we will start a new kind of programming paradigm called logic programming with this. I mean, this is new for you because you have not yet studied any other programming paradigm except perhaps just the procedural paradigm. So, these logic programming languages are called declarative programming languages versus procedural programming languages like C, C++, etc. These are declarative because you just have to specify in a declarative form what you want to do without actually specifying how the program should execute. You are not specifying how the program should execute. You do not have things like if, then, else, for, which specify the control flow. Control flow is pre-specified. You only declare what you want to do, right. So, this is called a declarative programming style. So, we start by looking at some basics. Firstly, we have the notion of instantiation, which is similar to first order logic. So, you can have predicates like likes Harry school, which is a fact because Harry and school are given constants, likes Ron broom, and then you can have rules of this form where you have likes Harry X if likes Ron X. So, here in prologue this is a sub goal, and in order to satisfy this sub goal you have to satisfy these, right. In other words, the implication is from the right hand side to the left hand side. So, it says likes Ron X implies likes Harry X. So, if you have to deduce what Harry likes, then to use this rule you have to first deduce what Ron likes, right. And we can have many other predicates on the right hand side. So, you can have likes Ron X comma eats X something, right. We will see more examples. Now, let us see that what is the notion of instantiation here. We can instantiate the left hand side, the rule head, with this predicate, right. So, you can have likes Harry school and you can have then likes Ron school, no, is the other way now, right. So, from this you should be able to deduce that likes Harry broom. Why? Because this is going to instantiate with this right, broom with X, and therefore we will have likes Harry broom. Now let us consider some goals and see whether we can derive that. Can we deduce likes Harry broom? Yes. How do we do this? Let us see how prologue will do this. It will start with likes, it will start with the goal. So this is backward chaining, it is always going to do backward chaining. So it will start with likes Harry broom. This is how we specify a goal, with a question mark followed by a dash. Then it will try to see what are the rule heads with this which will unify with this. So if you look at the rule likes Harry X. So the monkey and banana example, this is from the book of Russell and Norvig. This goes as follows. There is a monkey at the door of a room. In the middle of the room, a banana hangs from the ceiling. The monkey wants it, but it cannot jump high enough from the floor. Recall that the banana is in the middle of the room and the monkey is currently at the door of that room. Also at the window of the room there is a box that the monkey can use. It is actually besides the window, and the monkey can push the box to the middle of the room, then climb on the box, and then it will be able to get hold of the banana. The monkey can perform the following actions. It can walk on the floor, it can climb the box, it can push the box around if it is besides the box, and it can grasp the banana if it is standing on the box directly under the banana. We will define the state of what? State of the affairs with a fourth tuple which gives us monkey at, which is the position of the monkey, right, whether it is on floor or on box, then the position of the box, and whether the monkey has been able to, whether it has the banana or not, right. This is the state. Now like in first order logic, we are allowed to have functions in prologue.